Okay, so today we have Antoine. We have pleasure to have Antoine Deza as a speaker of the Tutte Colloquium. So let me just briefly introduce Antoine. Even so, for many, I guess he doesn't need any introduction. So since 2004, Antoine has been at McMaster University, where he held Canada Research Chair in combinatorial optimization. And since 2008, he has been the head of Advanced Optimization Laboratory and the director of Mac Data Institute since 2018. He held faculty positions previously at Tokyo Institute of Technology. He has been the chair of the Fields Institute Industrial Optimization Seminar since 2008 and the associate editor for Discrete Applied Mathematics and Optimization Letters. He was selected as a Fields Institute Fellow in 2014, and recently he became a Distinguished Fellow of Zuse Institute in Berlin. So today we have a pleasure to listen to the talk on kissing polytopes. Thank you.
Thank you very much. It's always a pleasure to be here. No, pleasure, no. Yes, I'd like to speak about something. By the way, so my co-author also, Sebastian Pokutta, is from ZIB, that you just mentioned, and Shmuel Onn from Technion, and Lionel Pournin from Paris. So what I want to show you is some property about polytope, but which is motivated by some application in optimization. What we try to do is the following. Okay? So the input is two polyhedra, either defined as a convex set of vertices or by inequality. We'll look at both cases. And let's assume they are disjoint. Right? They are disjoint, therefore there's some distance between them. Right? And I'm wondering, under some condition, how close can they be? Right? If you have no condition, you can make them arbitrarily close, of course. But let's take this case, where the simplest case, where we know the vertices are subset of the cube. Right? So this is the cube. So it's a 0, 1 valued vertices. Take the convex cell. Let's say I take these two guys, 0, 0, and 1, 1, 1. I take the main diagonal in dimension 3. I get an edge. And I take a diagonal in one of the facets. So let's say 0, 1, 0, and 1, 0, 0. I get two segments. And I can compute the distance between these two. Right? Now I could have taken something else as a purple guy. I could take this triangle. Right? I'll get the same score. So we have 2 to the d vertices, all possible subset, don't intersect. It's well defined, the minimum distance between all possible pair of disjoint P and Q. Okay? I'm wondering, so if you're wondering how far away they can be, for sure, 0, 0 alone and 1, 1, 1, there's something like root d as the distance. They can be quite far. But how close can they be? Okay? And how they look like? And so, for example, in dimension 3, you can just compute it, or by inspection, and see that this is the minimum distance is this pair. Okay? And the distance will be something like 1 over root 2. Root 3. Okay. So how this question came to us? It came actually as an element of something else. I don't know if you know this von Neumann algorithm. So you have two convex bodies, not the same polytope, and you want to check if they intersect or not. And if they don't intersect, you want to find the minimum distance. So this algorithm from the 30s, what they do is they take a point in one of the set, let's say in P, they project into Q, and they keep on projecting this way. Right? So there's some convergent stuff, and either you have a point which is in both, it's convexal, or you find the minimum distance, and you have a separating hyperplane, which is orthogonal to this guy. Okay? Now, in the way of Brown, Pokutta, and Weismantel, they revisited the classical von Neumann algorithm, and they replaced this projection, which is expensive, by doing a linear optimization call. Right? So they did something, and they get to complexity that either output a point in the intersection, or these are disjoint, the certificate of disjointness. Now, intuitively, if the guys are very, very close, it will be harder to, and they don't intersect, it will be harder to decide that they don't intersect, right? So it's not too surprising that someone in the complexity to decide if it's disjoint, to determine if it's disjoint, this quantity will occur, the distance between P and Q, as a square, as a denominator. Right? So that's why they were wondering, how small could it be? Let's say here, since we choose to have only 0, 1 polytope, the only parameter is the dimension d, right? So the minimum depends only on d. If this is something like 1 over d squared, 1 over d cubed, 1 over d whatever. So how small can be the distance? Okay. So it's what I want to address. Okay. So before doing this, I want to recall a few results of the same flavor. They are different in some sense, similar in some sense, but let's discuss this. So one of the key issues is, do we take the convex hull or the affine hull? Right? If I only want to discuss the distance between the affine hull of a point of a bunch of vertices, basically I get unconstant optimization, right? And I can solve it relatively easily by saying the gradients equal to 0. If it's convex set, it's a bit harder. Right? They might be like this or like that, distance change. Okay. So let's first look at this one. So this was defined by Javier Pena in this course. So it's a facial distance of a polytope, only one guy. There's no P and Q, but only P. Right? So you give me a polytope P, right? And I pick some vertices forming a face, an edge, maybe of a dimension 2, or dimension 5, whatever, a face. Right? For any face F, I take the guys here, I remove these guys. What remains as vertices, I take the convex hull. So I get a disjoint remaining guy called V minus F, is convex hull. And I take the distance between F and what remains over all possible F. Right? So all possible segments, what remains on possible dimension 1, dimension 2. This is called the facial distance of P. Okay? They use it in their work. Okay? Now we'll change a bit these things, which is similar. It's called this is from Beck and Stern. They look at also in the algorithm, they look at the same quantity occur. So what it is here, the big difference, it's the same facet, right? But here I take the affine F, right? So it's a big, so you might be far away, but actually the affine space is very close, right? So it's kind of unconstant optimization, while here is constraint. And we'll see it will be a difference, okay? Good. Now this result from Alon and Wu. So what it is, again, it's the same line. So here, it's a facet, vertex facet distance, so it's affine, right? What do? You take a 0, 1 polytope, and you pick a simplex. So you pick a d plus 1 point of your cube. You get a simplex, and you look how close the vertex can be, right? But how close in the sense of affine, right? So they might be actually, in some sense, far. So my simplex is the base of my simplex. It might be quite far, but if I extend the affine space, it can be very close. Much, much closer than the distance between the as polytope, right? So this result, so they showed something like a root to body. Okay? So again, this is in spirit, they do affine, while here, Javier Pena, he does convex. So here is, yes?
It's always L2 distance.
Always?
D is always with respect to L2 distance.
Yes. Yeah, because it's a bit when you think about von Neumann, they won't do it on the distance. Yeah, only L2. Correct. Thank you. Okay, there's something else I will not mention. It's related stuff. Okay. Now, what we did, so first, in a way, we were convinced that this thing is known. So first we checked that if anybody looked at this before. And so we could not find, so what we can prove, we say, okay, the distance is at least something, a small number, which is a root d power 3d, which is very small. And the way, I will show you the way we obtain this, it's a bit brutal in the sense that we are thinking, okay, we are over brutalizing it. Actually, it should be not that small. What surprised us even more, that actually we were able to construct guys who are very close. So actually, this number can be extremely small. It can be extremely close to root d power root d. Okay? So we are going to exhibit this guy. Okay? So in total, so at the end of the day, we have this result that basically it's root d power something and root d power root d. This is the result I want to show you and where it comes from. Okay. So once you know this, you can revisit the facial distance, right, which is the minimum between a polytope and its face. I can choose P to be the remainder and Q to be a face. It will give me a bound for the worst case of the facial distance. I just plug in what I have before and I get this. For D large enough, the minimal facial distance over all possible choice, you just plug P and this facet will be this. Okay. As a byproduct, we're able to understand a bit better how small could be the facial distance. Okay. Now, and I will show you this. I took 0,1 to make the thing simpler, but you can do 0,1k. I mean, you can do the same. Let's say half integral polytope, 0,1,2. Also, if it's defined by hyperplane, this x less than b, we have similar result. Right. Okay. Now, this is overall what I want to tell you, and I have to give you a bit of intuition how it works. So let's look in dimension 2 to start, to get some intuition. Okay. So what I do, I'm in dimension 2. I have only 4 vertices. So up to symmetry, either they are both segments, or one is a segment and a triangle, a vertex and a triangle, or one vertex versus segment. Okay, so the vertex we can always assume is 0, 0. Vertex, I will get 0, 0, 1, 1, get root 2. Now, if I take two segments, distance 1, right? If I take this segment and this one, it's a point half, so I get 1 over root 2. And if they intersect, it's 0. So if I take all possible choices, I will leave 4 values. Now, if I take them disjoint, I exclude 0, and therefore I define for 2 the minimum is 1 over root 2. Okay. I just have a notation here. So 1, because I'm forced to be the 0, 1 cube. 2 is the dimension, is 1 over root 2. In general dimension, if you take the point 0, 0, 0 and the simplex made of 1, 0, 0 and this permutation, you are 1 over root d, right? So 1 over root d I can achieve easily. But let's see what we have. Here the point I want to make is that the minimum is achieved by a guy not a vertex, which makes sense. But when you have two polytopes, right, and let's say you want to have the minimum, the likelihood you should at a vertex is not so big, right? It's not surprising. Okay. We can't assume it's a vertex. Okay, so 1 over root d for any d. Let's do in dimension 3 now. So again, you take a vertex alone, all possible segments. All segment could be the main diagonal of this one. If you do it by inspection, you will see the minimum is achieved 1 over root 6 by if you take the main diagonal of the dimension 3 and the main in dimension 2. Okay, you get 2 segments. So I'm saying in dimension 3, the closest it can be is 1 over root 6. Okay, let me just do in dimension 4. Yes, first, again, P star and Q star are not, there's a minimizer, are not vertices. And now you can also, if you have two segments, you can try to say, will the same be true in general dimension? Take all possible pair of segments in general dimension, and you can see that you always get 1 over root 6. It doesn't go small. You just parameterize by lambda and by mu, and you minimize these things. So the intuition is that if your polytope P and Q have a low dimension, they might not go that close. Right? Probably they have to grow in dimension, in some sense. Okay. Now in dimension 4, or in general dimension, so I can only draw in dimension 3. So this is the level last coordinate equals 0, so x equals 1. I take 2, so this is the guy in dimension 4. I keep the main diagonal as before, so 0, 0, 1, 1, 1, 1, and I take the first simplex in dimension -1, so I have a 0 here all the way. I permute the 1 here, so I get this kind of simplex here. And this is the main diagonal. This construction, you can check, you will get 1 over d more, 1 over root d at d minus 1. Same as root 6 in dimension 3. So you get closer, 1 over d, let's say. Can we do much better or not? Okay, so again, that's our first upper bound. It's at least as small as this number. Okay. To improve this, I need to make a construction which are much, much closer, and to get a lower bound. You cannot, what is the lower bound that you cannot pass? A threshold, right? Okay. You can compute and get some value to see how it goes in first dimension. I will show you how to do it to get a field. Okay. Now, so as I was mentioning, improving the upper bound would be to find two gain junctions are much closer, but obtaining a lower bound, or to prove something is at least something, we have to use a different technique. So I will start with a remark, which I relate to a very cool result from Steve, something some years ago, I will say. And what is it? Is this following one? So P and Q, let's say they are 0,1 polytope or 0,1K. They are rational polyhedra. Then the square of the distance is rational. So Steve, for something much more general, because it is any quadratic over polytope will give me a rational solution. We are going to look at it specifically. So the norm, the square norm, is a specific case of being quadratic. We are not going to use this result because we want to have a direct proof. Because we need something, we need to have something more than rational. I want to have a score, how close they are. Okay. So I will give you a geometric intuition for this, which is much simpler, and I will find back as a byproduct that the square of a distance between rational polytope is rational, and some other extra property, and I will get something. I guess that Steve will also give it too. That not only the square of the distance is rational, but the coordinate of P star and Q star are also rational. And they could be, why not P and P minus 1, the difference will be 1. No, each of them has to be rational. Okay. So, I will show it's rational, so it's very close to what you expect. There's some gradient equal to 0, and somehow the coefficients are equal to 0, and therefore are rational. Therefore, you use Cramer rule to get rationality. And then, so it is rational. And then, I'm not going to give detail, but somehow we will show that you have a matrix. So you have a score, you divide, you apply Cramer rule, you have a discriminant. You want to use Adama inequality to show that this guy is at least that big, at most that big. You use integrality to something is bigger than 1 on top, and you get this score. Again, I don't want to go into detail, but it's technical, but it's not difficult. If once you see it. So, but when you use Adama inequality, when you think about it, it's quite brutal. You know, you say that you ignore all the geometry and you say it's less than something. It's not that tight, right? Adama inequality. And somewhere I just say an integer is equal to 1, where it could be much more. So we get this score. Okay. Good. Okay. So now we have this lower bound, and we know 1 over root d minus 1 by what I showed you before is 2 segments. Okay. So I want to get to exhibit polyhedra who are much, much closer. Okay. So here I want to give you a bit of intuition and how it goes. So when you have a distance between two objects, at some point there is P star and Q star, was the minimum distance, right? And now you take the vector P star minus Q star and take the orthogonal hyperplane, it separates perfectly and you project this way, right? So what it means, if I rotate my space like this, I'm at P star and I look up, I will see Q star. And what I will see is that Q star will belong to the relative interior of a face. And the other way around, right? So let's say you take these two segments, the minimum will achieve at this vertex with the relative interior of himself and this way. In some sense, they are above each other. They're not like that once you rotate in the right direction. I'm trying to say that you will be in the relative interior of a smaller face. Okay? Okay. That's why you can apply. This gives us rationality, right? Because somehow you see when you're relative interior and above each other, you can apply just as the gain is equal to 0, and you get a linear system of which P star and Q star are the solution. Okay. Now something else. So how to put two polytopes very close to each other? So I don't know if you work often with 0,1 polytope. but they are quite rich objects. They're very a bit counterintuitive. And the idea is the following: is that if I chop off a polytope by an hyperplane, how many vertices do I meet? Can I get a lot or not? So the idea will be this one. So let me take, for example, 0, 0. Let's say sum of the coins is equal to 1. Sum is equal to 0, I get only 0, 0. Sum of the coins is equal to 1, I get all the unit vector, 1, 0, 0 in the permutation. Sum is equal to 2, I get 2, 1, and 0, 0, so I get D choose 2. Right? So just if I go to 3, to 4, no, to K, it will be D choose K vertices. So it grows a lot and lot. This kind of layered hyperplane perpendicular to the main axis. What's the distance between these two kind of slice? So distance between the slice equal to I and the slice equal to I plus 1. 1, right? So you see it's not exactly 1 or a bit. I have a lot of slice, right? I mean, I have a D slice, right? I have this, I have a D plus 1, it depends if you count all of them. If there is one in between, I will get D as a distance. And between 0, 0 and 1, 1, 1, the distance is root D. So it will be difficult, I mean, you have to force your way, so maybe it's a bit less than 1. So what's the distance, right? How to see the distance between two objects when you think about it? Right, so the distance is what? Is maybe, no, sorry. You take the normal vector, the common normal vector, right, which is perpendicular, and you take 1 point from your set, 1 point from the other, and do scalar product. Right? That's the distance. Right? Now, among these points, I can take 0, 0 if it belongs to, I can take just here, and then the normal vector, I can read it here, right? So what I'm trying to say, maybe it's not clear, let me, is that since they're offset by 1, the distance is nothing else than the normal vector 1, 1, 1, 1, its norm, inverse. So it's 1 over root D, the distance. It was close to this, but I mean, so. Okay, and you put D of them, you get D divided by root D, you get root D, which is the distance from 0, 0 to 1, 1, 1. Okay? So the point here I'm trying to make, I don't know if it's clear, but what you want to do, you want to make this vector tiny, right? Or very big, if you want to minimize the norm. So you want to make a vector which is very steep, right? So ideally I will put 1, 2, 4, 2 to the D. If I could do this and still maintain distance 1, I will have 1 over 2 to the D, right? Or D to the D, if I could do even better. Right? But you want to have a very steep vector here, okay? So if you think about, if I come back to what we do in optimization, minimize under x less than b, it's the same question as, I have an hyperplane defining my feasible region, and I know my vertices are all 0, 1. What can you tell me about the normal vector of my inequality? Can it be huge? Can it be small? I mean, by huge, I mean normalize them, kind of constant number, the ratio between the largest possible coordinate and the smallest one, right? I mean, between this guy, let's say we always put 1 here and all bigger than 1. Let's forget about the right-hand side. Can I make it very, very, very twisted, right? If I know my vertices are 0, 1, what can I say about my matrix, my inequality? It's the same question, right? The dual sense. So can we take a 0, 1 cube, slice it by some vector, maybe not this one, something a bit more complex, get a polydra, another one, in such a way that the vector A is far from being 1, 1, 1, 1. It's something like D, D squared, D to the D. If we can do this, we call it twist it, and we'll have this score. Okay? So this is what we have to achieve. Okay. So you can do something, you can achieve D power D. Okay, I have to alternate sign, because since I will go through x equals 0, if I don't alternate psi, I will have only 0, 0 as a solution. Right? So my vector will be something like that, 1, 1, 1, root D, minus root D, minus root D power 3 half, and something like that. So I have D time root d times, so in total the length is d. And starting from 1, the last one will be of order root d power root d. So it's quite a steep vector. And then you say, okay, I want to check which 0, 1 vertices satisfies this one. You have many, many vertices, satisfies this one, and then change to 1, you get another set. And they are very, 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 very close, because there's a 1 here, but A is very, very big. Okay? So, there is a large, so you have to carefully select the point to get something nice, and then eventually up to symmetry. Huh?
Sorry, but there's no 0, 1 polytopes.
Yes, 0, 1 polytope, yes. Yes, it's 0, 1 for sure. But you have many, many 0, 1 polytopes satisfy this one, right?
So you just slice that.
This is, I'm just using x equal b, right?
So you want to say that P defines slice and hypercube with this hyperplane is
P is exactly the convex hull
of 0, 1 vector.
of 0, 1 point vertices who satisfy x equal b.
Or P is convex hull of 0, 1 point that satisfies that. Because
Yes.
at the moment it's written like slice of the hypercube.
So yes, so it's so this hyperplane will cut the 0, 1 at vertices, which are 0, 1, right?
Right.
And this,
We have non-0, 1 vertices, that's what I want.
you have a lot of 0, 1 vertices.
Not 0, 1.
0, 1, 2, you mean?
No, whether it has vertices that are not 0, 1.
Ah, no. You know, if you take a convex hull of 0, if you take 0, 1 guys, their convex hull, their vertices are always 0, 1.
That's correct, but that's not, it's in a description. It's not.
Oh, I see.
Out a description, not in a
Okay, I see. Okay.
So A can have negatives?
Yes, of course. It has a lot of negative. Otherwise, you know, this system can solve it. It's 0, 0, 0, 0. The only 0, 1 guys who satisfy. Yes, it's X such that. Okay, P will be the convex hull of the point like that.
of 0, 1 points.
Yes. P. Okay, let me. Maybe I will answer you better. This is the set of vertices of P. This is a set of vertices of Q. It's 0. Okay, there's a segment here that disturb you, right? Yes. So there's a lot of negative coefficient, right? Otherwise, I will get no, it will not work. All good? Okay. And then, so now you have to kind of believe me in good faith. You take some guys, you take the symmetry, you remove them, you take some stuff, you sum them up, and you have to check this. It's a bit painful because you have to check that the lambda is sum up to, you have a convex combination and sum up to 1 and whatever. It's a bit technical, but at the end, you can exhibit P star and Q star from this set. So maybe not the minimum, but this guy are at distance, one of these guys, the order, right? I don't claim that it's absolute best, but you get the order 1 over root d power root d, which is close to, I mean, not so far from the Adama bound, which is root d power 3d. Okay. You can do a bit better, actually, with some alpha, but I just wrote it this way, so that you get an idea of what we are doing. Okay? Make sense? Okay. So I should you change that. Now you want to do it for 0, 1, 2 for anyone. So I will spare you, but it's kind of a variant of it. You can actually plug in the k everywhere and get the formula for 0, 1, 2 polytope. Right? Of course, the bigger you do it, the more choice you have, the closer you can get. Both numbers will go down more and more. Okay. The Adamar bound works the same way, and the constraint works the same way. Okay. Okay. Let me skip this one. Let me go down to the next one. So now, discrete optimizers, they often know the vertices for max cut, whatever. But many problems we don't know the vertices. We have the description as a facet inequality. We have x and b. We don't know the vertices. So I want to have something similar when my feasible region is given by the inequality. Right? So we use, in this case, we have different parameters than the size of the vertices. We use, what's in the Schreiber book, the new and the phi, which is the encoding length of the inequality, right? So it's a bit size, if you want, of any vertices less than this, and phi will be the encoding of the inequality, right? Okay, so again, I just use this notation because it's convenient. And then, again, I don't want to bore you too much, but you get, it's getting a bit more, less aesthetic, let's say, but the distance can be more or less bounded both ways, this way. Adama will go and the conditional will go. Okay. So, now to, again, go back to the bit of intuition. How to compute this number, at least for small dimension. So, if you want to generate all possible pair P and Q, it's a bit prohibitive. First, we have too many vertices, too many subsets, and then you have to check the intersect or not, and for each pair to compute the distance. Even using symmetry, it's a bit difficult. So we need to do something a bit smarter. So, first remark is that we are looking only for the minimizer, right? Not for all of them, so I want to reduce my set. If two polytopes, if I take the half in hull, so I have two triangles, I take the entire half in hull. If they intersect, or they don't intersect themselves, can I remove them? Can I exclude all polytopes that the half in hull exclude? And the answer is yes when I look for the minimum, because they're going to be actually orthogonal compared to this PQ minus P star minus Q star. They will be in parallel plane, right? So right away when I generate my guys, it's just an easy linear algebra. I can check that my guys, if I take the kernel, it's don't intersect. Okay. So it's just to say that at the end of the day, your minimizer will belong to two parallel hyperplanes, not just the one I constructed as an example, but in general. Okay. So the half in hull needs to be disjoint. Now, another thing I can, so at the end of the day, so you minimize, and P belongs to a face. P star and Q star, to a face of your polytope. I can always take actually a local simplex that capture my point. Right? So actually, I can always assume that P star and Q star, P and Q contain P star and Q star, are local simplices. Okay? Now, there's another argument to use that if both of them are out of big dimension together, you'll get something not optimal. Meaning that, let's say, if I'm in dimension 4 here, I need to have, in total, 6 vertices. So let's say 4 and 2, 3 and 3. So the number of the simplex, both of them should sum up to the dimension plus 1. So dimension is minus 1. The number of vertices in P plus Q will be D plus 1. So meaning that if I have in dimension 4, I can limit the size of, I can involve only 5 vertices, one guy alone versus 4, 2 versus 3, and that's it. They sum up to D plus 1, and they are disjoint. So this allows you to reduce singularities of the search space, and then you can use some symmetry. You can always assume that P is less than Q, stuff like that, and you can start to compute things just to check. Because all what I showed you before, these constructions are in very high dimension. To achieve this vector, you see, root D power root D, I cannot do it in dimension 10 or even 20. I need this to be a very long vector. Okay, so just to show you, so using this, we can do some computation. And so this is what I show you. So I took 1 over this, so 1 over root 2 in dimension 2, 1 over root 6 in dimension 3, and so forth. This is in dimension 1. And now you can, let's say, k equal 1 and the dimension increase. Or I can fix the dimension 2, let's say, and increase k. Right? I take a 2 by 2, 3 by 3, 4 by 4 box. Okay. So you get this number. So we don't know the general formula for k equal 1 for the dimension. When you look at this number, it looks like what? So for example, 5 is what? If I don't make a mistake, is 4 plus 1 Yes, yes. It's 1 square plus 2 square. Sorry. I know I should not. So, I mean, 1 square plus 2 square. 13 is 2 square plus 3 square. So it's a hard part. So anyway, so 25 is 3 square plus 4 square. So it looks like root of k minus 1 square plus k square. And it's true. So this, in dimension 2, things are easy. You can actually generate the formula. But even in dimension 3, we have to look at it. And for in arbitrary dimension, in dimension k equal arbitrary dimension, what we did, we have a bit more value. We plug it into the, I've asked many people did it. You go to the Sloan online encyclopedia, you put your number, and you hope this formula is known. There's a formula which corresponds to the first entry, but so far we could not prove it. So, but we hope it would be cool to have a formula and to know what kind of guys achieve the minimum. We have some intuition, but not too sure. And that's it. I will stop here. Thank you.
Thank you for the talk. Are there any questions? I will come with the mic.
Thanks for the nice talk. So I mean, a dual problem would be where you write the polytopes with, or polyhedra with linear constraints, where you bound the integers that can appear in the constraints.
Yeah.
Is that an interesting problem? Do you do your results apply to that, or?
It is an interesting problem. If this is a question. So you want to bound which part exactly? So you want to bound the entry to describe the polytope, right?
Yeah, the entries of, so AX less than or equal to B, and I want to bound the entries of A and B.
Right. So this is I see. So it's I see. So this here we bound the size that I see. Interesting question. That would be my answer. Yeah. Yes, I think.
Yeah, sorry. Just going back to Kostia's question again. How do you prove that the vertices of the slice you constructed are all 0, 1?
No.
Yeah.
So I will come back to the question with an answer, with the same answer. We take all the 0, 1. We take only 0, 1 point who satisfies the inequality.
And then you take convex hull.
Yeah.
And that's not necessarily equal to the slice of the continuous cube.
So do you cut or not an edge, right? This is the question.
Yeah.
Right? I mean, it's the same question.
Yeah.
Yes. So I will not say anything now, but do you cut?
I guess it's just quite close to the real.
Yes. So it's really at the corner. Right? Really very close to the corner.
But I guess like the convex hull of 0, 1 points would be very close to the real slice.
Yes.
That would be
Yes.
so.
Yeah.
Yeah.
Because the design is the same, right? I mean, yeah. So, same question, same answer. We take so you have this equality. You look for the 0, 1 guy satisfying this equality. So, which is of course computationally impossible, very hard, but by the symmetry of the stuff, we can generate many of. So there's Gaussian of them. There's easy family, say 1, 1, 1, 0, 0. Because so here, I mean, your question. I'll just give you a minute an answer, maybe to this one. Why we do this?
Yeah.
Because you can sum them up. All of them together contribute for one guy. So, and you let 0 somewhere else. So it's kind of way to partition your number into subset. And you get, by permutation, you get many of them. But not all of them.
Oh, right. Thanks. Yeah.
No, I saw.
Actually,
you're wondering if you cut an edge, yes.
I had to prove that exactly in a different context.
Yes, which one?
I mean, I couldn't prove it. So I was thinking about the simplex method at some point, and I had some slice of the hypercube, and I wanted to prove that all the vertices are 0, 1, and I couldn't.
But sometimes it's true, but in this yes, you have to. Yeah. No, so you cut an edge.
Yeah. Right.
Okay, so I mean, not only one actually. Yeah. Okay. Cool.
So in your example for, I guess, the lower bound for epsilon,
Yep.
What is it, 2, 1? Yeah, just...
Let me go back.
Sorry, epsilon d comma 1 I meant, yeah.
Yeah.
It seems like it's there, like the lower bound is that you get is for like very low dimensional polytopes, P and Q. So is that
Yes.
I mean, is that always going to be true, or is that just a...
So I'll try to answer your question properly. So you need, so both of them should be, so if both of them are dimensions is bounded, let's say you're in dimension d and they are at most dimension 10, it will never make it. You have to sum up to the sum of dimensions should be d minus 1. Now the issue is allowed to have, let's say, one guy of dimension 0, a vertex, and dimension d. It will not make it either. A vertex alone, any vertex alone can be, where is it? Merde, I need to find it, sorry. Forgive me. Yes, if you take a vertex alone, the closest you can get is actually the simplex, at level 1. The hypersimplex at level 1. So, what is not clear, so should they be both of dimension d divided by 2 more or less, or not? And this we are not too sure. I don't know if it clarifies things, but if we could take two main diagonals of the cube, they will intersect, so they're not good. But if I keep the main diagonal and I perturb the other one a bit, it's 1, 2, then they could be almost there. So by moving a few points. So, and you can achieve it maybe by taking two guys of dimension d divided by 2. But I have no proof about this. It's something we are trying to prove. No. But if both are fixed dimension, it will not make it. For example, 2 segments will be at best 1 over root d times d minus 1, which is very poor compared to 1 over root d power root d. Yeah. So somehow one could believe that the P star and Q star, I don't know, I'm just inventing now something, that P star and Q star, as a limit point, they are the center of the polytope, half. You know, both of them are going to this point. But I don't know. I'm just saying, yeah. You are deep inside, very, very deep inside. Thank you.